basically, we built an autonomous vehicle just to say that, yep, we've got it. Now, the exciting thing is in May of 2018, so in a couple more months, we're going to launch our Ohmio Lift, which is a 20-seater autonomous vehicle built right here in New Zealand. The first one's already been sold to Christchurch Airport, so we should be seeing that over there. Now, when we talk about autonomous vehicles, there's a lot of different classes there, and when people say autonomous vehicles, you need to sort of split that up into different categories. So there's actually a level system that goes up from 1 to 5, actually goes from 0. Level 0 autonomous vehicle is one that's completely driven by a human. So technically, even if your vehicle is not autonomous, you have a level 0 autonomous vehicle. So you can go home and just tell everyone that. Level 1 is when we're looking at things like cruise control, automatic braking. Level 2 is when those things combine. Level 3 is when the vehicle starts to drive mostly by itself, but when it gets into an emergency situation, it basically goes, I don't know what to do, you take over, to the driver, which is really scary. And there's a lot of people who think that level 3 should just not happen, and we should skip automatically to level 4, which is autonomous in some environments and expected environments. And then level 5, which is seen as the holy grail of autonomous vehicles, is a vehicle that can drive anywhere at any time with any sort of hazards that's in front of it. So most of the companies that you see are chasing that level 5 vehicle. But as we saw from the news a couple of weeks ago, it doesn't always end well, and there's a lot more left to sort of research in there. So we see a lot of opportunity in level 4 vehicles where they operate autonomously but in expected environments. So what we want to do is basically build an autonomous tram that follows virtual tracks that we'll be able to modify via software or from the cloud, and they'll choose new tracks based on demand, and if there's a new construction zone, they'll move right around it. But I'm going to stop talking about how awesome our vehicle is, and maybe I'll talk about let's see how AI helped us solve a problem. And I think that's a much better sort of way to explain how AI is important to companies like ours. So we'll use the case study of localization. Now, localization is a robot's, not even a vehicle, a robot's understanding of where it belongs in the world. So the world, or the map that it has, can be anything. It can be the universe, it can be the earth, it can be a little warehouse if that's where the robot's deployed, and that's all it needs to know. And an autonomous shuttle, if you don't have localization, the shuttle's more or less useless. It doesn't know where it is, doesn't know where it needs to go. It's just an expensive sort of glass box that people can get in and sweat. Not exactly the best sort of thing that you'd want to build. So this is something really important to us. We need to get this right. So on our Ohmio Ohmio hop, there's a little white puck at the top, and that's the GPS. And that GPS receiver basically works like any phone or any sort of GPS device that you've got. Now, how the vehicle sees a GPS signal is that it'll come in as lots of different little guesses about where it is. And there's always some error involved in any sort of sensor that you have on a device. So in this case, they're all sort of clumped around one little area, so we can say that this is generally where the vehicle is. So this is why if you go out and you look at your phone and it's trying to tell you where you are, it'll sort of drift around a little bit. That's because of this uncertainty. So this is our test track. So this is the HMI Technologies office, and there's a church next door, and we like to go on the footpath autonomously and get into their parking space. So what happened on this trip was it was all going fine, and then suddenly the track it didn't know where it was, and then it all returned to normal afterwards. So I went out there and took a picture, and this is the part where the GPS basically flipped out. So when it passed under those branches, it sort of lost line of sight with GPS satellites and was no longer able to triangulate its signal properly. So what that looks like from the point of view of the vehicle is that these points are starting to come in on a lot larger area. They're still accurate, but they're not precise. And when you're trying to stay on a footpath, an error area of that large is not going to go over well. So what can we do? We asked both our engineering team and our AI team the same question. Our engineering team's suggestion, bless them, Very, very practical people. Technically right, which engineers pride themselves over, but we can't do that. We can't cut down every tree that we come across. Maybe the tree's a building, maybe it's a native tree. Doesn't work. So our AI team said sensor fusion. This sounds great. And that is a very cool word, but lots of people don't know what it means. And so let me explain it to you. So what's sensor fusion? This is how the GPS, is how the vehicle understood its location. The GPS was directly plugged into the vehicle's understanding of its location. When the GPS went haywire, the vehicle's understanding of location also did the same thing. But what a sensor fusion module would do is it allows many different types of sensors, including a GPS, to be plugged into one module. It fuses that sensor data, sensor fusion, and that's when it culminates all of them into one understanding of where the vehicle location is. So, what sort of sensors can we use? First is odometry. So the vehicle knows what speed it's going at and what the turning steering angle is. So it knows that in a second's time it might be there, but the speed that it has might be a little bit off. So it could be there or there. Same with the steering angle, it might go a little bit left or it might go a little bit right. But you end up getting sort of this error area. So this area, we can say that with probably 95 probability the vehicle's going to be in there. Another thing we can do is get LiDAR. So LiDAR sounds super futuristic, and if you've never come across the word, that's also fine. Basically, it works like if you've been in a submarine, or if you're like me and just watch spy movies, and you have these little radars that go around and basically send out radio and sound waves, and it bounces off of objects. We can do the same thing, but with a laser. So the same sort of rangefinder that you get from Bunnings or somewhere like that, but we stack like 16 of them on top of each other and spin it around really quickly, and we get a point cloud. So that's a 3D representation of what the world is around us. And from that, we can do some pretty awesome stuff. So a vehicle does its little rotation, and this is a very simplified version of what it sees, but this is the point cloud that it gets. Now, how do we place it in the world? Say that this is the world. It exists of 4 trees on this single PowerPoint slide. Where is the vehicle? The computer or the vehicle ends up guessing millions of guesses about where it might be. So it makes some guesses that are wrong, or hopefully this is always going to be wrong. We don't want a vehicle to end up in a tree. But this is not a good candidate location because none of the features around match up with any of the features on the map. So it makes another guess and says, maybe the vehicle's here. This is better. There's 3 features that match up. A better guess, but still not great. There's a lot that aren't matching up. So probably the vehicle is somewhere around here, or this is one good candidate location. So we've got our error radius. It might be, the LiDAR might be a little bit off. So how do we put it all together? We've got our GPS with our error radius around it. We've got our odometry with its error around it, and we've got our LiDAR. And when we put, even if the GPS sort of blows out underneath the tree, we can still place the vehicle because we've built in some sort of redundancy in the system. So that's a typical sort of example of how the R&D team works together at Ohmio. We've got when we come across a complex problem, we give that to our AI team. The AI team breaks that problem down into mathematics. From there, they put it into an algorithm, whether they need to make that algorithm themselves or implement one that already exists. And then they build a proof of concept. So this isn't a thing that is ready to sort of be shipped, but it's just a proof that, hey, we can actually do this. The engineering team then takes over and implements that proof of concept inside the vehicle. And then both the implementation or engineering team and the AI team work together to try to optimize it. So when we first had our sensor fusion module, it ran maybe once every 5 seconds, which is very bad for a vehicle. But we managed to optimize it to run once every few milliseconds, which is the area that you want to be in. Now, is there a perfect input type? No. Every sensor has its drawbacks, and it's classic engineering where everything is trade-offs. So the sensor fusion really helps plug in those holes where one sensor might fail, the others can pick up the slack. So GPS obviously fails with occluded sky, odometry and steering gets compounded errors, and the LiDAR, maybe someone's parked a car where the wall used to be. So why do we keep developing? And it's that R word that I said before, redundancy, which is a horrible word if you're thinking about your job, but it's a great word when you're thinking about safe engineering systems. So what it means is there's different types of technology all doing the same job. And when that happens, that means that if one of those technologies fails, the other ones can pick up the slack. And your technologies are going to fail. You just need to mitigate that risk as much as possible. So I like to think of it as slices of Swiss cheese. You know how Swiss cheese has holes in it? So every type of input has a hole in it. And if you stack enough slices of Swiss cheese, as long as the holes aren't in the same place, you get a solid block, or what appears to be. So that's the Swiss cheese model. But from doing this, we can do things like not have to rely on the GPS at all. We can get rid of the GPS and just navigate indoors completely, which is actually something that we've done. So this is an example video. This is our test vehicle. This was our first vehicle, but now it's what engineers use for testing. So here we've used GPS and what's called ultra-wideband beacons. So we built our own sort of indoor GPS, not based on LiDAR or anything. So outdoors, the vehicle will use GPS and it navigates fine, didn't go under any trees. But then once it goes indoors, it switches, or the ultra-wideband starts to kick in. And that's when the vehicle can go inside a warehouse and know exactly where it is. And then it can pass out as well, go directly outside. And once it goes outside, of course, the GPS starts to kick in and it gets an even better understanding of its location, because now you've got two sorts of input types all working together. And pretty much that's how you get a vehicle to navigate indoors. Thank you.